So hi, and welcome to this first online meeting for MTH129 Discrete Maths. Thanks everyone for coming, whether you're coming live, which is good for you people here, or if you're going to watch it a recording later, thanks very much. So basically what I'm going to do for each of these weeks is I'm going to ask people for questions in advance, anything they really would like to cover, make sure I do that. Otherwise, I will work through topics from the week. In particular, I'll try to focus on what would be covered in the tutorial session that the internals get. Um, but not necessarily, I won't necessarily always hold to that. Just looking at things that are the trickier parts. So in particular, today, the tricky things this week is really about the idea of being countable, uncountable, the infinite aspect of it. So the finite sets and being able to combine them still requires practice and work, of course, but perhaps a bit easier to get on your own. So I will look at some of those because they are still important to go through, but focus more on the infinite side of things to begin with. I just want to clarify my expectations of some of this set notation. And so the lectures so far have been pretty formal in terms of the presentation of set theory. I just want to make it clear to you guys as well, do some examples that I want to be more pragmatic. I'm happy for you to be pragmatic about set theory. And what I mean by that is you can use write down sets in a way that other people can understand. You do not have to use all the fancy notation yourself. Now, depending what you read, when you look at reading other algorithms, etc., people will use formal notation for sets and logic, etc., a few times. And so it's important to be able to read it, but I'm more than happy for you to write it in a much more natural way. So please hear that message loud and clear. So it's all about thinking about the audience you have to communicate it to. Okay. So basic plan. Ask questions as you need to. So interrupt whenever you need, etc. Okay, so I want to start with just a basic questions. This is from the exercises from tutorial 1, and although I'm going to start simply, it just shows you what my expectations are for how to write these sort of things down, and then it also quickly links into the more difficult concepts of how to classify the sizes of sets, whether it be finite or infinite, and what type of infinite it is, and just explore that a bit. So let's just do them as they stand. So let's just do 1b for the moment. So I'm just doing them out of order. And what I want you to do is actually want you to have a go. So it's not just about you listening to me all the time. So people who live today, can you type in the answer for 1b in the chat box? Now I want to talk through it while people are having a go. Basically, what set notation means is chuck things in curly braces. So what I really want to do, sorry, I'll just make the question clear. I want you to use set notation, just for the moment, use set notation to write down what 1b looks like. And then we'll worry about the classification in a second. So I should make the question clear. So what I'm going to do for each of A, B, and C, just for the moment, is write down each of these English sentences in some sort of set notation. So for 1b, set notation really just means writing down things in curly braces. So have a go. What can you do? So there's options. I want to discuss those as you start thinking about what you might want to write down. The options are you can just write down all the numbers in it, which is what someone's done in the chat box. Thank you very much. Now you're much more diligent than I am. What I would do something different than that, but anyway, you could write down all the elements, which is what someone's done. So you could write 1, 2, 3. Instead of you could write down every single one. Another option is to go, well, if anyone else is reading it, they'll be able to see the pattern, and they can use ellipses, so 3 dots, to say, oh, that's what the rest of the pattern is. So if you can see the chat box, people have typed it up much neither one I've written down. Both of those are good, right? Both make it really clear what the set is, and both other people can understand it. So those are really nice, clear ways of identifying it. And again, that's probably the best way of answering how to write it in set notation. You can also put it in set builder notation, which I'll just put down here. So basically, we've got a bunch of elements such that, so this vertical line means such that. So x is an integer. So that's basically what we've got. And then we have some condition. So it's that x is between 1 and 20. Or you could write it down like someone's got there, between, exactly as in the chat box, so x is strictly between, so 0 between 0 and 21 exclusive. That's also fine. And you can write this as x is in the set of natural numbers, which are right with the double in. So they're all fine. So they're all good. So the 3 great answers there. So thanks, guys. What's the best one? It doesn't matter. It's about communicating which is easiest to communicate. I would suggest that, I suspect for many people, this first one's probably going to work quite nicely and that'll be fine. It's important, though, to understand set builder notation because it's good to be able to read it, but also because sometimes you have to do it. So let's just look at some other ones. Okay, 1a. So for 1a, you have to write down set notation for the set of odd integers. So what ways are there of doing that? Well, same sort of approaches apply. You could just try writing it out directly, or you could try set builder notation. And both have their uses. I'm just curious to see what people are going to write down themselves. So set notation uses curly braces to start with. So it's set of odd integers. So you could write it down. Now, there's actually an infinite number. So one way of writing it down would be just to start listing them. And then once you work, when you think you've got enough of the pattern, just put dot, dot, dots. So what someone's put in the chat box, I wouldn't put an end on it, so it just keeps going forever. That's one way of writing it down. So that's just basically just listing all the elements. And you have to use ellipsis in this case. You can use the set builder notation if you don't like that. So x, and again, let's use the fancy one. So a bunch of all the natural numbers such that x is odd. And you could write that in English if you wanted to. Or sometimes, if you actually want to do anything with this set of odd numbers, it's nice to know what x is odd means mathematically. So x is equal to, say, 2n plus 1, where n is another natural number. Would be another way of trying to specify it. So just trying to clarify, this little e symbol here means in. This n, which I'm writing with the second line doubled, it means the set of natural numbers, so 0, 1, 2, 3. So just non-negative integers. It's a long way of saying it. So which of those notations better? Well, the first one's fine. That's perfectly acceptable. If you want to do anything with these odd numbers, sometimes this last one is good at least to understand that that's what it's about. But I'm really happy, like you got marked right in assessment items, just doing these simple approaches. Now let's look at 1C. So 1C is a set of real numbers between 1 and 20. Now, in this case, again, you might think, we could either just write them all out in a list, or we could use set builder. But if you start trying to think about real numbers is just another way of saying decimals. You're going, well, I can't really write these decimals down in a list. Like, where do I start from? Well, I got 1. I know where to start from 1. But what's the next number? What's the next real number? It'd be 1.0000. We'll keep going. There's a 1 somewhere along the path. There really is no clear next number. So you can't really list them all like that. Now, as soon as you realize you can't write in a list, that tells you something. By the way, it tells you that it's an uncountable set. More on that in a second. But you can't really list them in this case, so you really have to use set Boolean notation. So in this case, we've got a bunch of numbers. They are real. So you could say in English, like x is a bunch of x's such that x is real, or using fancy notation if you like it, x in the set of real numbers, such that x is between 20 and 1 inclusive. And you could, as I said, you can say x is real. And as I've made a few times, I'm happy for you to be a bit fluid about exactly how you do it. It's just about so other people can understand you. So as you can see here, although for sometimes you can just list all the elements, you can't always get away with that. So you definitely need to know how to do set Boolean notation if you need it, essentially. And the vertical lines mean such that. Now, what I want to do is classify each of these 3 sets now as either being finite, countable, or uncountable. So I just want to talk a bit more about that before going back through that. So basically, this is all talking about the size of a set. So the fancy word is cardinality. So if you get a finite set, it's pretty obvious. I mean, the size of the set would be just how many elements there are in it. So out of A, B, and C, which of them are finite? So just tell me which ones are the finite sets. And if the finite sets, what's the size of them? What's this cardinality of them as such? Don't be shy. So just say A and number, whatever it might be, or B and a number. Thank you. I can see, and I presume you can too, when someone's typing, you can see it. It also happens when someone bumps buttons on the keyboard as well, which you may not intend to do. So I get false positives, but people tried and they didn't do it. Okay, so I can tell you, as someone wrote down for 1B, you can actually write down every single element. And so for B is finite. Thank you. So thanks, Bruce. So B is finite, and there's 20 elements. You can just count them, 1, 2, up to 20. With A and C, the fact that I had to use an ellipsis for 1A when I write it down, and the fact that there's lots and lots and lots of decimals between 1 and 20, that these A and C are infinite. And so you have to do something else. So for finite sets, it's normally clear. You go, I could just write them all. If I was patient enough, I could write them all down, and I can count them. There's just 20 of them. So that's a finite set, and the cardinality is clearly 20. A and C are infinite. So for infinite sets, talking about the size of them is a bit trickier. So, and the answer is the size is not just infinity. There are different types of infinity, I guess. So, can I try to nut down what really we mean by this? And so what he said, so what the definition is that 2 infinite sets have the same cardinality, same size, if there's a 1-to-1 correspondence between them. So, for example, I could have a set containing all the harmonic numbers, which is 1, a third, so 1 1/2, a third, a quarter, a fifth, etc. So, and it's infinite set, so there's lots of them. So all these different fractions 1 over them. So they're called the Egyptian fractions. Is another way for it. So what I can do is if I can have a one-to-one correspondence of these to some other set, so an obvious set that this matches up to would just be the positive integers. Every number I can map onto it. That's what a one-to-one correspondence means. So for every number in the first set, I can name one the other one, and there's always one-to-one, so everyone matches up. There's a nice one-to-one correspondence between this set we'll call H. And this one over here, which is the positive integers, which you can write different ways, but n plus is the notation I use sometimes for it. So the positive natural numbers. So this is a one-to-one correspondence. So other words for this one-to-one correspondence is called a bijection. And bijection means, why the bi means two, so it goes both ways, means you can go backwards and forwards. So it's just a way of linking the two together. That's what the word bijection sort of suggests. So if you've got a bijection or one-to-one correspondence between two sets, any sets as a matter of fact, that have the same size. Finite, don't really have to worry about it. It's a bit overkill, but for infinite sets, that's really a useful way. And so basically what Cantor worked out is that, I guess what he said is there's sort of two sorts of infinite sets. So there's the countable ones, and that's basically same size or cardinality as the set of natural numbers. And you can take, if it's infinite, so you can take one or remove one. So I think textbooks puts it just the positive integers. And uncountable is the rest. So not same size as n plus and infinite. Now I should make myself a little bit more clear in this case. So the definition for uncountable is true. So uncountable means it's an infinite set, but it's not the same cardinality as the set of natural numbers. Countable depends on who you're talking to. I would use the word countable to suggest finite sets. So I'd say finite sets are countable, but I really want to say countably infinite means the same size as n plus. So really, basically, so this definition of countable really just splits all infinite sets into just two groups. Just saying, do they same size n plus or not? And if they're, and in some sense, the countable means that's the smallest. How Cantor described it. This is the smallest level of infinity. So if you go to infinity, that's the smallest level of infinity. And uncountable are bigger senses of infinity, so bigger amounts of infinity. Now, this is getting a little weird to describe it all. So what does it mean in practice? How can you I would like to just be able to look at some sets like a B and C here and just tell quickly which one's countable, which one's not. So does this set here, looking at 1A for example, the question we still got is, well, is that countable or not? Does it have the same size as the natural numbers or it doesn't? Well, the basic way of doing it in practice really is if you can write all the numbers down in the list, it's countable. If you can't write them down in the list, it's not countable. That's really what it boils down to. So although it's all about bijections, that's how you really do it in practice. So the fact I can write down the set just by writing all the numbers down in some sort of order as a list like that, that tells straight away to me this is countable. So let's write them down. So that's finite. That's countable. Or countably infinite. Now, often to try to prove it's countably infinite, you have to just tell us what that bijection is. That really just means telling you that's, and really the bijection is what the position is here. So, making it clearer. So we have to write a bijection between the set of odd numbers to the set of natural numbers. This is, we have to do a one-to-one correspondence bijection. Well, you go, well, I'll just write down the numbers, 1, 2, 3, etc. in order, and basically that's the bijection. If I can write a list down, that automatically gives me bijection straight away. That's it, really. Now it's used for the formulas for it all. So sometimes the formulas are complicated, and knowing it's just easier to say, oh, it exists. If I worked hard enough, I could tell you what it is, but it's clear that it exists, and I do that sometimes. But in this case, it's not too hard. So in general, an odd number looks like 2n plus 1. That's sort of general form for an odd number. To work out what the matching number would be in this correspondence is basically just getting n. So this first one is so that's right. Let me just fix it up so I'm actually telling you exactly the truth. 2n minus 1 would be more accurate. Sorry. So that's what the general form of an odd number is, 2n plus minus 1. So 2n minus 1, as I've written it down. If you just match it to n, that's just the natural bijection in this particular case. But in practice, countable infinite means you can write down as a list, and as soon as you got the list, the order in the list just tells you what the bijection to the positive natural numbers is. And that's the end of the story. So with 1c, for example, we couldn't write it down in a list. By writing down the smallest element in the set's 1, that's the first one you write down, but it's not really clear what the next number would be. If you think of a number bigger than 1, so if you can think of any number bigger than 1, I can always tell you another number between it and 1. So for example, if you think of 1, think of another number. Think it's a number, say 1.1. Well, I can tell you a number halfway between the two. We think of 1.00001. Well, I can always find a number halfway between. There's always more and more numbers between it. And so in some sense, you can't list them like that. And as soon as you can't list them, it means it's uncountable. So this is an uncountable set. Now you can prove that officially. So you can actually prove that there really is no bijection, one-to-one correspondence between a subset of an interval of real numbers, like this one here, and the set of natural numbers. So that is provable. So the textbook does a few of those sort of things. So it's called, essentially, most of those proofs really hinge around what's called Cantor's diagonal argument, which appears in many guises. So it's the similar sort of proof works in most of these cases. So the way to prove most things uncountable is to use that sort of approach. I'm happy for you just to identify it. I guess that's the end of the day. Okay, now is that clear to people? Is that clearer than what it was? So that helps you identify them quickly what it is, and helps you quickly identify what the bijection is for a countably infinite set as well. Okay, off. Solved for one person, so cheers. Now, so this was developed by, this idea of countable versus uncountable was developed by a Cantor who lived a bit more than 100 years ago. And so a guy, Hilbert, a very famous mathematician at the time, was just trying to understand some of the things that he was developing. And so he came up with so Hilbert did lots of great things. So he also came up with just a nice visual problem of trying to communicate this idea called his Hilbert's Grand Hotel. And so basically, this is a way to try to understand countably infinite sets, and just try to show that they are quite different intuitively to what you think of as finite sets. Now, it's just a metaphor, and if you listen to my lectures from Monday, there were some people heckling, which is fine. I don't mind that. They were doing it in a nice way, but heckling about just how they're trying to push the metaphor and how it doesn't really quite match up. And that's true, that we live in a finite world. And so, Hilbert's Grand Hotel really is just a figure of our imagination. But it's just a way of trying to understand a bit more concretely. So it just recalling it for you in case you've missed the lectures and things like that. Hilbert's Grand Hotel is basically an infinitely sized hotel. It's countably infinite, as in the sense that every room has a number on it. 1, 2, 3, 4, 5. So really, just Hilbert's Grand Hotel is just a word and metaphor really for the set of positive integers. That's what it really corresponds to. And you can do different little exercises with it, just try to think of what some of the bijections might be between different sets. So just as an example, get the highlighter out. So this is the one I want to do. In the middle here. So State of Origin was last night. I don't really follow League very much myself personally, but it's certainly topical at least. Some people really do like it, so maybe you guys, some of those are. So let's assume that the Hilbert's Grand Hotel is full. So there's actually an infinite number of people sitting in there, and it happens to be half Queenslanders, half New South Welshmen, because there's a lot of interstate rivalry going on. The Queenslanders were put in the odd rooms, and the New South Welshmen were put in the even rooms. Now it's the end of State of Origin, so they've all gone home, or the Queenslanders at least. Olivier ANZ Stadium, and so now the occupancy rate of the hotels are half, I guess, if you would put it that way. And manager doesn't like that. I mean, hotel managers like to have high occupancy rates, and so they just want to rearrange the hotel so it looks full, or it is full. And they've asked you to make it full. How do you do it? So I have a think. If you can explain it, you can explain it simply actually. You type in, but while you think about how to do that, I just want to talk about the maths behind this problem, what it's really asking for. Essentially, when the Queenslanders have all gone, what you're really left with is the occupied rooms are just the even numbers, so 2, 4, 6, etc. So that's really the occupied rooms. And what we want to do is we want to move these occupied rooms into the new hotel, which has room numbers 1, 2, 3, etc. So what I'm trying to do is I'm trying to show that 2, 4, 6, etc. The set of even numbers is countably infinite, and I'm just trying to work out what the bijection is between this set and the set of positive integers. So that's what it really boils down to. So these sort of problems with Hilbert's Grand Hotel are really just trying to explain what sort of sets are countably infinite and talk about in a bit more of a word picture sort of way what their bijection might be. That's what they correspond to. Just trying to help us grapple some of those sort of things and understand what's different about infinite to what's other stuff. So now as soon as I can write down like this, the sort of answer becomes clear. And the answer is, well, the way I managed to get all the hotel full again is I ask each New South Welshman who's in whatever room it is, just to move to the room in the half their room. So I won't write it down, but basically, if someone's in room 2, get them to move to room 1. If someone's in room 4, move to room 2, etc. So if someone was in room 2N, get them to move N, and that makes the whole hotel full again. Now, that wouldn't work with a finite hotel. So if you had 10 rooms and half the people left, you've only got 5 people, and no matter how you move them around, you've still only got 5 people. So with infinite, if you've got an infinite number of people there, then you can just shift them down. There's always more people further along the line you can shift down to fill up the space. And that's the funny thing about infinite. There's always more along. But to make it easier to handle, we need to be able to count them. That's the idea of countable infinite. So countable infinite is much easier to handle. So just an aside, you go, I don't really know why we have to worry about countable and uncountable, really. Well, let's go to computers. So this is This is the application of computers. Let's do two sets. So the first set is the set of all computer programs. So tell me a language, computer language you guys like. I don't really care what it is. So what's a computer language that you guys like to use? So Java. Okay, so let's put Java in here. So let's write, this is a set of all possible Java computer programs. And so if you think of Java as being, so the source code, so all different types of source code you could ever write for Java. That would include ones that work well, ones which are complete utter junk, ones which, let's make them syntactically correct, so ones that would at least compile, but other than that, so just anything that would compile, who cares what it actually does. So that's a set of Java computer programs. So this thing here is countable. I'll have to try to justify it. That's a countable set. Can be infinite, by the way. So what I mean by that is, one, there's an infinite number of programs, so I guess that's believable. So if you want to make them, so you could always just have, you can have as many lines of code as you want to, and so you can always just say, define a variable a and make it equal to 1, as many times as you want to. It doesn't really do much, but that's always possible. So you can have as many lines you want to. That will quickly make it infinite. Why it's at can be infinite is you could write them all in a list. How you do that is each Java is really just a bunch of tokens. So each keyword or identifier, for example, just a token. If you just have some sort of, you can define an order for the tokens. So there's just a few keywords and a few special symbols. There's not many of them. Give an order to that. And if you have any variable names, just put them in alphabetical order, for example. Then you can have an order. So pretty much any Java program really is just a bunch of tokens, and you'd have all the programs of the shortest length first, shortest number of tokens first, put them in alphabetical order. Next you have the next bunch of length 2, length 3, etc. I can't mention too many length ones, but that's the idea. So you could put them all in order. It is possible. So it's countable infinite. Let's write a different set, and this is A. This is the set of all algorithms that you might want to do. Okay. I'll explain a bit more what I mean. So this is the set of all different things you might want a computer to actually do. So what does a computer do? Really simple terms. So an algorithm pretty much is, you've got a bunch of states. So you've got input, and so the input can be described as, say, the set of natural numbers is all the different. So you can have lots of different states. And so for this online meeting we're doing now, the states are the video camera, which is actually recording lots and lots of information. It's the audio of me and everybody, you, all the mouse clicks. There's actually lots of input just for this online meeting. So it's a lot of inputs, but you could write down all the different possible states. And so you can write a countable number of possible states you can possibly be in. So that's the input. An algorithm then would, no matter what input you give, it would produce some sort of output. And the output would correspond to all the different output states. So in this case, what your monitor looks like on your screen, or the audio comes from your computer, what's happening in your registers, all that. So the output's quite considerable. There's lots of different options possible, but essentially an algorithm really is just a function going from inputs to outputs. So A here is uncountable. Now, I'm going to wave my hands around to say that. So it's uncountable. I'm not going to, I could try to justify if you wanted to. So the set of all possible outcomes is uncountable, that you cannot list them all. that the number of functions here is much bigger. So what does that tell me? Is that all the things that we might possibly want to do in a computer, these are all the different algorithms you want to do, cannot be done because there are more algorithms out there than there are Java programs, or pick any language you want to. There's more algorithms, many more algorithms possible than what there are computer programs able to handle it. So that tells me that some algorithms are not computable. So there's some algorithms that you will never be able to get a computer to solve for you. And so famously, in case you're going, well, give me a practical example. So an example of an algorithm which is not possible to do is called the halting problem. So it's not possible to write a computer program that would be able to check any computer program, so any Java program, for example, to always be able to make sure that it will not have an infinite loop. So any halting problem is, if you could solve the halting problem, it means you could write a computer program that it would be able to check Java code for you and be able to tell you for sure if there's an infinite loop or not. You can't write that program. It's impossible, theoretically impossible to write that sort of one. So that's an example of an algorithm that's not doable. So that's an important difference between countable and uncountable. So that's the theory of computation for you. And so that's work due to Turing. So and Turing machines, if you've heard of those, look more into that. So anyway, enough about infinite sets. Let's just go back to some of the simpler stuff, perhaps. And that is looking at Venn diagrams. So basically, when I look at these sets, I mean, we are mostly going to deal with countable ones. That's, after all, a computer really has a finite number of states. A computer program just finite length. And so what it ends up being is there's always countable number of computer programs, countable number of states in a computer. So really we're dealing with countable stuff when we're dealing with computers. That's what we're going to focus on. But we still need to be able to talk about sets. That's just a nice underlying language for it all, about to combine them. A useful way of understanding them is Venn diagrams. So you can do lots of algebra for it, but I think Venn diagrams tend to be a bit easier to handle in most circumstances. So I want to just show you some illustrates here. So this is question 3A. Now, if you can type these in your chat box, you're doing fantastically, I reckon. So I'll have to do some of them. So I did do 3A in lectures, but just want to cover it again just before I do the more complicated ones, just to remind you. So a Venn diagram pretty much is you write a box for the universal set. So pretty much we're assuming that all the elements we're possibly going to consider sit in some sort of universal set. So for a computer program, that would be for a computer that would be all the possible outputs the computer might ever produce, etc. Normally, we're just going to make it really simple. It might be just a set of integers, for example. The box is the universal set. Every set is some sort of object in it. So I can only write in circles. Now, if I want to draw a Venn diagram for some general expressions like this, I would like to make sure I cover all theoretically possible scenarios. So all possible overlaps. Now, for two sets, that just really means write it as two overlapping circles. That's fairly straightforward. But I'll come back to the other ones, what that quite means. Now, I want to just colour it in. So A minus B is really just understand indentation. That's everything that's in A but not in B. So that's everything in A here, but not B. So it looks like a Pac-Man is how I describe it, or a circle with a byte taken out of it. That's what A, and this bit I've coloured in is A minus B. So now I've talked about the special case. Let's do 3B here. So I've got three sets, A, B, and C. Now, as I said, I want to make sure that all situations are possible. So that's two sets. Now, the third one, I want to be able to have all possible overlaps happen. So in order to draw that, I really need to draw them a bit like a triangle sort of shape. And so at first glance, some people attempted to write it down as in a line. I'll just this is the mistake. So write it down like that sort of way. So what's wrong about that approach is you're assuming the outside two circles, two sets here are disjoint. So that means that you're assuming they have no overlap. That may or may not be true. And so you're adding extra assumptions. And so what I want to do here is I want to produce the most general result. That's why I'm using this middle diagram. That's just worth clarifying. Okay, let's just try to color things in. So I want A and B minus C. So how I would actually try to color this in is I do it one at a time. So I'd work from the inside out. So B minus C is the inside part. So I've got B and C. So B minus C pretty much, as of the picture over here really is everything that's in B, but not C. So that's that part there. Then I want and A. That's everything in A. So A would be this section here. That's that circle. So this cap symbol means intersection. I really think it's just best wording as word and. So I want A and B not C. So I want to see everything that's common between these two. So therefore, this part here, this little section here, is common between these two bits I've coloured in. So the bit in common here is A and B minus C. Incidentally, that would also be the bit of A minus B, so the bit that's common between A and B minus C. So they are the same. So, I mean, but that's sort of how you do it. So, like I said, really just stepping in at a time. So let's just let's just do E here. I'm going to do them all. So we're looking at A intersection B bar, or so union or A intersection A and B. So there's a quite complicated expression here. Now, if you're comfortable enough, you perhaps could do it all on one picture, but it might be easier to draw it as separate pictures. So there's only two sets, A and B. So A intersection B would be everything that's in A and not in B. So that would be everything that's in A and not in B. It's A and not B. Now, again, if I'm going too fast or I'm saying something you don't understand, just stick your hand up, so to speak. That's the first bit. That's that part. So how I'm really tackling these expressions is just going inside out. So just doing the inside part first, which is how that's how a computer would have to work it out. It has to go from the inside expression out. So then the other expression is A and B. So that's everything that's both A and B at the same time. So that's the overlap between the two of them. So and really just in terms of diagram means what's the overlap of these two different sets. And then what I do is I want to do the or bit, the union part. So the union part really just means color both in at the same time. So I first got the A intersection B, that's that part there. So I'm coloring that part in, and I'm going to color in the A intersection B part. So I'm going to color in both parts in. So that's what I end up colouring in. Now, I think probably need to make it clearer. So I know it's a bit easier to put the two together. Just so if you're trying to communicate this to other people, it might be good just to label the diagrams better. I'm using a bit of English words. So my question is, that's our Venn diagram. This is our Venn diagram. So basically the Venn diagram to correlation from that expression was the one I did before, actually when everything was all red. What does that simplify to? Using the Venn diagram, what would be a simplified version of that set expression? Any ideas? So I'll just color it in so it's easier. Like just put it all in one color so it makes it easier to see. So that's what the Venn diagram was. What's the simplified expression to what that picture looks like? Can you describe it more simply than, well, the first one had four different sets and three different operators and a bar over the top, so four operators. So it's complicated. Can this variable make it? Sorry. So isn't B bar a different variable to B? Is someone's question. They're related. So B bar means not B. And so I didn't do this, so let's just put on the side here. So this is B in the middle. Not B is the outside. So if I just do some colouring in here. So B's the middle part. Not B is the outside. So that's the relationship between the two. I would think of them as being the same variable. So B would be when the variable's on, B bar's when the variable's off. If you want to think in terms of a computer. So how all these things would work in one often way of thinking at these is in terms of logic. So how a computer would work, how it would be represented in a computer. B, if it's B, it's on. B bar, it's off. So same variable just set to either 1 or 0. That's one way of thinking about it. So same variable, just different state. Depends on your language how you want to describe it. It might seem funny to describe them as ones and zeros for this sort of set of stuff. But as we go through, you see that logic, binary representation in a computer, and sets are all highly related to each other. I mean, they have different applications, but the way you handle them is quite similar. So as I was discussing that, some people have told me the answer, so thank you. And that is, this here is just the picture for just A. So all I've just done is colouring A in. So I wouldn't put the vertical lines around it. That would suggest the size of A. And so what we've done is using Venn diagrams, we've shown that that expression is equal to A. So that's the combining property. So if you filter, so basically in order to, so A intersection B bar and A intersection B is splitting up A into when B is on or off. So it's splitting up into cases and then combining them together again. So this is really just decomposing into cases and then you can recombine them again. Okay, so the next question is, I got this expression here. This expression, sometimes you want to be able to prove these things. So it's nice. It's really handy to know how to simplify these sort of expressions. For one is, although you go, why would I know to simplify set stuff? The answer is you often might want to simplify logical expressions, which are very closely related to these things. And it's useful to know the properties for it. So in order to force you to actually engage with those, what I'll get you to do sometimes is ask you to prove those sort of things by different mechanisms. And sometimes you have to use symbols, and so you have to use a bunch of rules. Now, I haven't mentioned those in lectures yet, so I'll do them next week, and I'll talk about it next online meeting if you want to. Okay, so just using my other screen here for a second. Yeah, this is the Interact 2 side. If you go to assessment items, now something I put up there last night. If you go to if you go under exam, so just something worth mentioning here. For the exam, it's closed book, but you're allowed to bring in a double-sided A4 piece of paper. I guess a cheat sheet, one way people describe it. So formula sheet. You can make. I encourage you to prepare your own. I have put an example one here. So just going to open it up. So this is the example sheet. If you can read it from where you are, you're doing really well. On the second side of it, I've left a lot of white space here with the intention of you want to put other things on there. But I have put down lots of the rules. So if I just make it a bit bigger. So you might get a chance of seeing it. So some of the rules for applying sets are here. So this is De Morgan's law, for example. So De Morgan's rule pretty much states the relationship between doing intersection or so the opposite complement of intersections and unions, etc. So this is all the rules here. So the first 7 of them, I think it is, are the defining properties, and the bottom few, so the bottom 5 here, are implications of the first 7, or the first few. So these are implications. So they're the most common implications we use. So there are others common rules that get used at times, but I guess they're the default ones that I like you to use. So they're all listed there. That's all in one place. And again, you'll need to have access to that for your exam, either in your mind or on a piece of paper. And so my encouragement is to write on a piece of paper, so you don't have to remember every single one of them. So, what are the next? Okay, let's just do one more example just to think some things through. Okay. Sorry, I'm just trying to get my screen working sometimes so I can see the right window. This is another one for tutorial 1, so more just to try to think out loud. So we've got 2 statements here. I would like to either try to prove them or show they're wrong, I guess. So in order to prove something, proving stuff, as I'll talk more about next week, requires you to do lots of different steps that lead from the premise to the conclusion, essentially. So the premise here is this mathematical statement on the left-hand side, and the conclusion is B equals C. So proof means doing lots of little steps to go from one to the other. And each step needs to be big or small enough so the person reading it knows. So you can do big steps if the person can understand what you're talking about. You don't have to use little steps. And I'm happy for you to prove these things lots of ways. So you can prove them using Venn diagrams for this sort of stuff, or you can prove it using the rules of set notation, which is I flicked up quickly, not really using. To disprove something is much easier. You have to come find one counterexample. So one counterexample disproves it easily. So bringing it down straightforward, proving it's the hard part. So let's have a look at them. I'll just do the first one. So to try to keep us to the time. Not that I mind going over time, but you might have other things to do. And by the way, you're more than welcome to leave early if you need to, which I know someone has already, so that's fine. So let's do our general Venn diagram just to give a sense of what's happening. So I've got A, B, and C. And then we might want to so we know that A union B, which would be these sort of glasses shaped here, coincides with A union C. That would be the blue one. This is the red one. So I haven't drawn it that way, but that's what the conclusion is. So the union of them are two the same. Can we automatically infer that B and C are actually the same? And you go, well, let's just try to draw my pictures again. So I have to try to draw the unions together. That's A, and this is B. So I'm going to have to draw C, and I use a different color here. I have to draw C in a way so that the overlap's the same. Now, if you think about it, that really forces the boundary of C here. It forces C to be quite, would contain this part here, but it may contain more or less of the other part. So that could be an example of C. So just trying to show what the problems are is here. Is that as I've drawn this new picture, so I've drawn the first Venn diagram just to try to think about how this might play out. Like, it's not proving it. Like, as a matter of fact, it doesn't actually match the premise at all yet, but it's just a way of thinking through the problem. So I've tried to, now just trying to draw it properly. I've drawn A and B, and I've tried to draw A and C so that the two unions do match up. But as I'm thinking through, I go, I don't actually have to make B and C the same that way. So you can see I've drawn a picture here that the two unions are the same, but B and C are different. So I reckon this is not true. And so now I have to try to think of an example for it, really. And so now from my little picture, so the Venn diagram is my helpful way of thinking about things, is you're going, well, for this to work, B and C will have some common elements, but they'll have some ones that are different. And so you're going, well, let's just write that down. So let's give them a column element, make them both have one, and make them have something which is different. 2 and 3, for example, are things that are different. And then I want to make sure the union's okay. So therefore, A here will have to contain the things that are different. So just tuck 2 and 3 together. And I could add more elements, but that's probably enough, just a minimal counterexample. So this is a counterexample. Just think about it. A union B would be chucking these outside two together. They'll give you 1, 2, 3. So unions 1, 2, 3. If I chuck A and C together, these two, I'd get 1, 2, and 3. So the unions are the same, but you can clearly see that B and C are not the same. So that's my counterexample. Now, you didn't have to use Venn diagrams at all for it, but I think Venn diagrams are just a nice, helpful tool with many things when it comes to sets, just like truth tables are really helpful for logic, and they're related, fortunately. So it helps you give you a way of thinking through stuff. So thanks for coming to the class, and I hope to see you guys next week. If you have any questions in the meantime, just fire away via email or discussion boards. That's perfectly fine. And I'm happy to answer questions, any more questions you have now, but I think I'll leave it there. If you do too much, you start losing concentration after a while. So you guys need to go through and do some more practice yourself, of course. So I encourage you to try the exercises from the study guide in particular. And there's also extra ones in the textbook. And these ones here are from what's called exercises 1 under the class materials. So thank you very much, guys.